Hello everybody, welcome back to another Big Ideas Algebra 2 lesson. Today we're taking a look at section 5.3, which is going to be all about solving radical equations and inequalities. We've learned just about everything there is to learn about these at this point. We know how to transform them, we know how to use them, we know how to do basic operations with them, but now we are going to learn how to solve equations that have these in them. So the first type of example you might see is something like this, where you have an equation where there is an exponent somewhere in the problem. We know that in order to solve something like this, we will need to use reverse PEMDAS, and eventually we're going to have to undo that exponent. First things first. For this first problem, we're going to start by subtracting 12 from both sides. Reason is, we always get rid of addition and subtraction first. So we have 7x to the fifth equals 1701. Now, we want to get rid of any multiplication or division that we see. So let's get rid of this times 7 by dividing by 7. Those cancel out, and 1701 divided by 7 is going to give us 243. So x to the fifth equals 243. Now, from here, we need to get rid of a fifth power. And we know the inverse of taking something to the fifth power is taking the fifth root of it. So let's take the fifth root here on both sides, and we would find that x equals, if we plug this all into our calculator, 3. The fifth root of 243 is just 3. Now, whenever we decide to create a radical, like we are square rooting both sides of an equation, we always have to ask, is this going to produce one solution or a positive and a negative? In this case, since our index is odd, it's 5, our n equals 5, we know that we don't need to put a plus and minus, only if our index is even. Speaking of, what can we do for part B? Well, here, everything is in parentheses except for the fourth power. So we actually start by taking the fourth root of both sides. Now, what happens when we take the fourth root of both sides? In other words, when our index is even? We're going to get a positive and negative answer. We'll be left with x minus 3 equals positive and negative. Hang on a second. 48 is not a perfect fourth root, right? So what can we do? Well, we have to decompose the fourth root of 48, turn it into two different fourth roots, one of which will give us a number, and one of which will give us a remainder. In this case, some perfect fourth roots are 16 is the fourth root of 16 is 2. The fourth root of 81 is 3, but since 81 is a little bit too high, we know that we can decompose this into 16 and 3, because 16 times 3 is 48. So since the fourth root of 16 is 2, and we'd be left with the fourth root of 3, we say that the fourth root of 48 is 2 fourth root 3. From here, there's only one last step we need to do, which is to get x by itself. To accomplish that, we can add 3 to both sides. Now, when we write out our answer here, you could write it as plus or minus 2 fourth root 3 plus 3, but that's a lot of symbols all in the same spot. We usually like to put our whole numbers here, like 3, at the start. So it's 3 plus or minus 2 fourth root of 3. Just a general rule of thumb. There we go, that's our answer. Down here, though, we also might have radical equations. Equations where there is a root symbol somewhere in it. Again, we have to use inverse operations to solve. Just be careful. When you square a radical, you have to square the entire other side of the equation. Let's do example A here, and then I actually want to take a look at example C and leave B for you to do on your own. So, once again, we use reverse PEMDAS to tell us what order to do things in. This big radical can almost be treated like it's in parentheses. So we get rid of our minus 1 first by adding 1 to both sides. The cube root of 2x minus 9 equals 3. And of course, what's the inverse of cube rooting something? It's got to be cubing it, or taking it to the third power. We're left with 2x minus 9 equals 27, and this is much easier to solve. We just add 9 to both sides and divide by 2. Plus 9 gives us 2x equals 36. And then we can divide both sides by 2 to get our final answer, x equals 18. Unlike when we are creating a radical, like right up here, we created this fourth root, we don't need to worry about positive and negative answers here. We just get the answers we get. I'll leave B for you to try out, but I would like you to take a look at C. I want you to start C. Then, when you're about halfway done, pause the video and see how well you're doing. There's something we have to catch here that's a little bit different to what we've done in example A. Pause the video, try it out, and come back when you feel that you're about the halfway point. So we may have recognized that we want to subtract 3 from both sides, giving us the square root of 5x minus 1 equals x minus 3. So far, so good. And here, how do we get rid of this square root? Well, of course, we square both sides. This is where a lot of folks will make a mistake. First off, the square of the square root of 5x minus 1 is just 5x minus 1. But x minus 3 squared is not the same as x squared minus 3 squared. No, this is a binomial. We can almost write it like x minus 3 times x minus 3, right? Because it's x minus 3 squared. We have to think back to when we solved our problems with polynomials. We actually have to FOIL these two out, or double distribute. So when we do that, we're left with 5x minus 1, but it equals x squared minus 6x plus 9. And how do we solve an equation when there's x squareds and x's all over the place? We recall our goal is to get everything onto the same side first. So I'm going to subtract 5x and add 1 to get everything onto the same side. So we have 0 equals x squared minus 11x plus 10, and this can be factored. So what multiplies to make 10 and adds to make negative 11? Well, we know that that's going to be negative 10 and negative 1. So x minus 10 and x minus 1 are our two answers. We just have to actually get the x's out of them. X equals 10, x equals 1. Perfect. That is how we're able to decompose these problems. When you square a binomial, you have to FOIL it out, and you might get two answers. Very, very nice. From here, let's take a look at the back side, because there is something interesting that happens. Whenever you raise an equation to, well, specifically an even power, you once again produce the risk, or you run the risk of producing extraneous solutions. We talked about this last unit, but extraneous solutions are solutions you get which seem to work, like you solve for them, but when you plug them back into the original equation, you discover that they don't actually work. So let's look at our answers to 2c on the previous page and see if either of them are extraneous. As a reminder, we got x equals 10 and x equals 1. And I'm going to use the extra space I have over here to show you what we would do. We have to, step by step, plug in all of the answers we got and see which ones work. Since x is in two places in our equation, we're plugging 10 in, for instance, to both of those x's. So we could get something like 5 times 10 minus 1 plus 3 equals 10. We'll have to check to see if that works. Or we might also have to find 5 times 1 minus 1 plus 3 equals 1. So let's take a look at simplifying these. We can multiply 5 times 10 to get 50. Minus 1 is 49, so this is the same as the square root of 49 plus 3 is supposed to equal 10. This here is 5 times 1 minus 1 plus 3. 5 times 1 is 5, minus 1 is 4, plus 3 equals 1. Since the square root of 49 is 7, 7 plus 3 does equal 10. This is a good solution. 10 does work. 10 is not extraneous. But if we look down here, the square root of 4 is 2. And is 2 plus 3 1? Not so. So x equals 1 is our extraneous solution, which we mark by crossing it off. So our only answer is 10 for this one. Beware of extraneous solutions, as they are dangerous. Down here, for question A, we are going to talk about how to solve an equation that has two radicals. I would like you, however, to start off by crossing off B. When I made these notes, I did not realize that there was a critical error in it that prevents it from being solved, so you can cross off B. For example A, though, solving with two radicals is a lot like solving with just one. Your goal is to get one of the radicals by itself on its own side, then use inverse operations to get rid of them. You may have to square both sides or take the third power of both sides or whatever more than once, but for A we won't need to. So how do we get a radical by itself? We should start by moving this radical, 3x plus 4, to the other side. So let's add the square root of 3x plus 4 to both sides. These two are going to cancel out because it's negative and positive. And we'd be left with the square root of 2x plus 1 equals the square root of 3x plus 4. And from here, we know how to get rid of these radicals. To get rid of a radical, we square both sides. And luckily, this will actually cancel out both our radicals. We'd just be left with 2x plus 1 equals 3x plus 4. We solve by getting the x's on the same side, so we can subtract 2x. That'll give us 1 equals x plus 4. And then when we go through, we can subtract 4 from both sides, giving us x equals negative 3. But remember what we discussed. When you raise an equation to an even power, you run the risk of producing extraneous solutions. So let's just plug negative 3 back into our original equation and see if it still works. So we always do need to continue checking where extraneous solutions are. If we get x equals negative 3, we have to plug it into the original and see what we get. If we get something that we can't solve or something that doesn't make sense, then yeah, it may be that it's extraneous. In this case, if we plug in negative 3, we get 2 times negative 3 plus 1 minus the square root of 3 times negative 3 plus 4, and that's supposed to equal 0. 2 times negative 3 is negative 6. This is the square root of negative 5 minus 3 times negative 3 is negative 9 plus 4 is negative 5. The square root of negative 5 equals 0. And since we're talking about only real solutions, we don't have a way of square rooting a negative number. So what does this mean for us? It simply means this is going to be extraneous. We would say this is no solutions and call it a day. Now, when we're dealing with rational exponents, it's the exact same. We just have to undo the rational exponent, but it's a little bit trickier to determine what to do than with a radical. When you have a third root, you raise it to a third power. But what if you have something like a 3/5 power or a 2/3 power? Then we need to remember our rules about rational exponents. To undo a rational exponent, you want to take it to a power that will turn that exponent into 1, because that'll get rid of it. In other words, instead of raising both sides of the equation to an exponent which cancels a radical, we're raising both sides to that exponent's reciprocal. So if I gave you x to the 3/7 power, for instance, and we wanted to get rid of the 3/7 power, we wanted to undo it, we would take that to the 7/3 power. Our exponent rules say that we would multiply everything, right? So we do 3 times 7, 7 times 3. That's x to the 21 over 21, which is just x to the first. That's what cancels out a rational exponent. So always multiply by the, or I should say, take it to the power of the reciprocal. Also recall, if you raise both sides of a power to, or with an even denominator, you're effectively taking a square root, and you're going to get a positive and negative solution. So let's take a look at A. We're going to take a look at B, and we're going to take a look at C. For A, if we have x plus 30 to the 1/2 power equals x, we have to raise this to a power that'll get rid of the 1/2. That's 2 over 1. Is our denominator even? No. Our numerator is, but only if our denominator is even is that the same as taking a square root. So we raise both sides to the 2 over 1 power. That gives us x plus 30 equals x squared. We move everything to the same side by subtracting x and subtracting 30. We get 0 equals x squared minus x minus 30, and this we can factor. We factor this one as x minus 6, x plus 5. So our answers are x equals 6, x equals negative 5. Once again, we always have to check for extraneous solutions. So think, is 6 plus 30 to the 1/2 power equal to 6? 6 plus 30 is 36. 36 to the 1/2 power is the same as the square root of 36. So yeah, we get 6 equals 6. If we plug in negative 5, negative 5 plus 30 is 25. The square root of 25 is 5, but that does not equal negative 5 that we would have plugged in on the other side. So we say negative 5 is extraneous. I'd like you to try out B on your own, and then we're going to do C together again. So pause the video and try out question B. Hopefully you've had a chance to try this one out. We would start by dividing both sides by 3, since we always get rid of multiplication and division first. Reverse PEMDAS, remember? So we get x plus 1 to the 3/5 power equals 8. From here, to get rid of a 3/5 power, we should take everything to the 5/3 power. So we get x plus 1 equals 8 to the 5/3. No need for a plus or minus at the start because we don't have an even denominator. Our denominator is 3. What is 8 to the 5/3 power? Well, there's a tricky way of figuring it out and an easy way of figuring it out. We could do 8 to the 5th and then take the cube root of it, but that seems like it'll give a big number. Instead, remember that this is the same as the cube root of 8 to the 5th power. Again, this would be the same as if I was to write it like the cube root of 8 taken to the 5th power. And the cube root of 8 is 2. So what's 2 to the 5th power? 32. So x plus 1 equals 32, meaning our final answer, we subtract 1 from both sides, is x equals 31. We can plug it back in to make sure it works. So we have 31 in parentheses. 31 to the 3/5 power is 8, and 3 times 8 is 24. So we know that this is our answer. For part C, I wanted to do this one together because something's a little bit different. Of course, we still start the same. We still want to get rid of the 2/3 power by taking both sides to the 3/2 power. But remember our rule. If you raise both sides to a power with an even denominator, you're basically taking an even root. You're going to get 2 solutions. So while we get x minus 5 over here, we do have to put down positive and negative whatever 100 to the 3/2 power is. Again, we can think of this as the square root of 100, that's why we have a plus and minus, raised to the 3rd power. And since the square root of 100 is plus and minus 10 raised to the 3rd power, we get x minus 5 equals plus or minus 1,000. From here, we would need to add 5 to both sides to get rid of the minus 5, giving us x equals 5 plus 1,000 and 5 minus 1,000. Our answers are x equals 1,005 and x equals 995. Or sorry, negative 995. My bad. If you were to plug both of these in, we have to find out what's extraneous or not. If you plug in 1,005 here, that's 1,000 to the 2/3 power. That does equal 100, so we're good there. If we plug in negative 995 minus 5 is negative 1,000. Negative 1,000 to the 2/3 power. Hang on a second. That one is also going to be positive 100. So both of these are solutions. We don't have extraneous because both of them work. That concludes our lesson and our unit for today, everybody. So thank you so much, and have a fantastic rest of your day.